Well, my studies have already shown that the power radiated by a black body is dependent on the black body's temperature, and that the frequency and intensity of light are related in a complicated way. Now, if I can just get Stefan and Boltzmann to figure out the mathematical relationship for me again, I'll be set.
Professor Kirchhoff, we have a problem. I just spoke with Boltzmann and he can't get the mathematical equation to work. When he applied the same principles he tried to apply for the temperature-power relationship, he found that the intensity should constantly increase as frequency increased. But you and I both know this conflicts with the empirical data.
You sure he's done everything? This isn't just a mistake?
He's done all he could, he simply cannot get it to work.
This is a tragedy. Never before has observation so blatantly contradicted theory. It's a catastrophe, I tell you. Notified catastrophe.
Shock. Kirchhoff and the rest of the scientific community were completely baffled. Classical physics, which had previously served to explain every known phenomenon, suddenly seemed woefully inadequate. What was to be done? Had scientific knowledge come to a standstill? Would black bodies forever remain a mystery, an unsolved puzzle to science? The puzzle was finally solved by Max Planck, an enterprising young student of Kirchhoff's.
Eureka! No wait, that was Archimedes. Oops, hops, gefunden. I found it! We've always assumed that the energy of an oscillator was continuous. But what if it's not? What if it is discrete? Maybe in a reaction, a quantum of energy must be exchanged.
This was a revolutionary thought. Never before in the history of science had someone dared to suggest that energy was a discrete quantity. It worked, however, and Planck was able to reconcile theory and experimental data by assigning a proportionally constant to all energy values. Today, we know this value as Planck's constant. It is equal to
6.6260755 times 10 to the negative 34 joule seconds.
At first, Planck's theory was quite controversial. Many scientists were skeptical, including Planck himself. However, evidence continued to pour in until the one controversial quantum was a universally accepted scientific fact. By setting a precedent, Planck paved the way for a plethora of new scientific advances. Einstein, for instance, treated light as quanta to explain the photoelectric effect. As the name suggests, quantum mechanics relies quite heavily on the quantum. Planck's constant played an integral role in the measure of energy of a photon. The description of the Compton effect and de Broglie's matter waves, moreover, it was used to derive the Bohr radius and allowable energy levels in a hydrogen atom.
This will certainly have far-reaching implications to the scientific community. I wonder what its practical significance will be.
Although at first many of these scientific advances seemed far too theoretical in nature to ever be of much use to society, they eventually brought about a variety of technological developments, such as electron microscopes, lasers, medical isotopes, nuclear weapons, light meters, and semiconductor electronics. All of these technologies, whether directly or indirectly, resulted from Planck's revolutionary use of the quantum.
What an exciting discovery! I must go tell my friend Einstein.